So this is Bayes' theorem. This is Project 7, Group A4, EX 203. So what is the theorem? Bayes' theorem states that suppose that E and F are events from a sample space S, such that the probability of E is not equal to 0, and the probability of F is not equal to 0. Then, the probability of F given E is equal to the probability of E given F times the probability of F, all divided by the probability of E given F times the probability of F plus the probability of E given not F times the probability of not F. So now the definition of conditional probability tells us that the probability of F given E is equal to the probability of E and F divided by the probability of E. And also probability of E given F is equal to the probability of E and F divided by the probability of F. So to prove this theorem, we can use that probability of E and F must be equal to the probability of F given E times the probability of E, and the probability of E and F is equal to the probability of E given F times the probability of F. Setting these equal to each other gets us the probability of F given E times the probability of E equals the probability of E given F times the probability of F. Dividing both sides by the probability of E, probability of F given E is equal to the probability of E given F times the probability of F divided by the probability of E. Now, at our denominator is probability of E, we can simplify that a bit. We can show that the probability of E is equal to the probability of E given F times the probability of F plus probability of E given not F times the probability of not F. So, some properties of E. E is equal to E and S being the sample space. E is also equal to E and parentheses F or not F. E is also equal to parentheses E and F parentheses or parentheses E and not F parentheses. Thus, the probability of E is equal to the probability of E and F plus the probability of E and not F. We have already shown that the probability of E and F is equal to the probability E given F times probability of F. Also, we've shown that the probability of E given not F is we have the probability of E given not F is equal to the probability of E and F divided by the probability of not F, which shows that the probability of E and not F is equal to the probability of E given not F times the probability of not F. Now we have the probability of E equaling the probability of E given F times probability of F plus the probability of E given not F times the probability of not F. Finally, we have the probability of the probability of F given E is equal to the probability of E given F times the probability of F, all divided by the probability of E given F times the probability of F plus the probability of E given not F times the probability of not F, which is the Bayes' theorem.
Let's come to example 1. We have two boxes. The first one contains 2 blue balls and 7 red balls. The second one contains 4 blue balls and 3 red balls. Bob selected one ball by first choosing one of the 2 boxes at random. He then select one ball in the box at random. If Bob has selected a red ball, what is the probability that he selected a ball from the first box? In order to tackle this question, let's define the event first. Let E be the event that Bob had chosen a red ball. The complement of E be the event that Bob had chosen a blue one. let f be the event that he chooses from the first box. Let complement of f be the event he chooses from the second box. Then the question becomes, given E, what is the probability that f happens? Step 1. Find out what do we need to solve this problem. Based on Bayes' theorem, the probability given E, the probability of f given E will be equal to probability of E and f divided by probability of E. Step 2. Find out the probability of E and f. Since E and f are independent instants, assume Bob randomly chooses from two boxes. Hence, the probability of f is equal to probability of complement of f equal to 1/2. Then the probability of E and f equal to the probability of E given f times probability of f, which is 7 divided by 18. Step 3. Find probability of E. The probability of E is equal to the probability of complement of f and E plus the probability of f and E. We have already know the second part, so we come to the first part. The probability of E and the complement of f is equal to the given complement of f's probability, the probability of PE times the probability of complement of f, which is equal to 3 divided by 14. Then we will calculate PE equal to 38 divided by 63. The last step is calculated the probability given E, the probability of f given E. It is equal to the probability E and f divided by probability of E, which is 7 divided by 18 divided by 38 divided by 63, which is 49 divided by 76. So that's the answer of the first.
So the question is, in answering a question on a multiple choice test, the student either knows the answer or guesses. Let P be the probability that the student knows the answer, and 1 minus P be the probability that the student guesses. Assume that the student who guesses that the answer will be correct with probability 1 over m, where m is the number of multiple choice alternatives. What is the conditional probability that a student knew the answer to a question given that he or she answered correctly? In order to answer this question, we first denote some of the events. Let f be the event the student knows the answer, and E be the event the student gets the correct answer. So the probability of f given E is equal to probability of E given f times probability of f divided by probability of E. We know from the question that probability of E given f is equal to 1, while the probability of f is equal to P. So by Bayes' theorems, we know that probability of E is equal to probability of E given f times probability of f plus probability of E given not f times the probability of not f. So overall, we have 1 times f plus 1 over m times 1 over p equal to p plus 1 minus f parentheses over m. So the probability of f given E is equal to p over 1 minus p over m plus p, which, if we simplify it, is equal to mp divided by 1 minus p plus mp. For example, if m equal to 5, p equal to 1/2, then the probability that the student knows the answer to a question he or she answered correct is 5 over 6.